Hello, everyone. First of all, happy Diwali. And if you have given this contest, really proud of y'all that you guys are giving a contest on Diwali, which shows that you guys are dedicated. Okay. But with that being said, today we'll be looking at problems A, 2D of today's Codeforces round. Before knowing, before starting with the problems, I want to know how many of you guys were able to solve in the contest. You guys can put it up in the chat and we can start discussing. So let's start with problem A. All right. It's called circuit. So Alice has just crafted a circuit with N lights and 2N switches. Each component has two states. Okay. Now, what does all of this say? The states can be on or off. The lights and switches are arranged in such a way that each light is connected to exactly two switches and each switch is connected to exactly one light. It's unknown which light each switch is connected to. When all switches are off, all lights are also off. If a switch is toggled, the state of the light is connected to it will also toggle. Okay. So guys, let's understand what the problem had to say. So guys, if you look at it, the problem says that there are 2n switches. Okay. Let's say n is equal to 3 here. All right. And there are n bulbs. Okay. Let's say these are the n bulbs. Okay. Now, randomly, like there is no assignment given yet, but let's consider that every two switches is connected to a particular bulb. All right. Eventually, first, like initially, all the switches are off and they are denoted by 0. Okay. Now, when you turn on a particular switch, the state of the bulb toggles. It means that if it was on, it becomes off. And if it was off, it becomes on. We need to find, like we are given the state of the switches. We don't know what the assignment was. We need to find the minimum number of moves and the maximum number of moves to make all bulbs off. If we are free to choose these assignments, like how are they assigned to each particular bulb? Is this much clear for you all guys? Is the problem statement clear? Yes. Now, if the problem statement is clear for you all, let's analyze a few things. Okay. Guys, consider you have two random switches and you have a bulb. All right. Now, these switches can have four states, that is 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now, guys, do you agree? Here the bulb will be off. Here the bulb will be on. Here the bulb will be on. And here the bulb will be off. Yes or no, guys? Yes. Great. And guys, do you agree that in this case, where they are on, it will take me one move to off that particular bulb?
बोर्डिंग देखो 11:15 का ही है।
Guys, I would really appreciate if you guys mute yourself. Okay, amazing. Okay, so guys, if you notice all of this, first of all, we need to find the minimum number of moves. If we want to find the minimum number of moves, guys, do you agree that we would like to, okay, let's first find the minimum number of moves. Okay, to find the minimum number of moves, guys, do you agree we want as many bulbs to be off as possible? Off as many bulbs. Yes or no? This is the state that we want. Now, guys, consider we have the array 1, 1, this 0. Do you agree if we want as many bulbs off as possible? Let's do this. We would like to have these two together. We would like to have these two together And maybe then for these two, we can say that this is on, so it would take one move to make it off. Is this much clear for you all, guys? Yes. So our job is to just pair up the ones as much as possible. So in minimum number of moves, guys, we would like to pair up all the ones as much as possible. And if there is a one which is remaining in the end, can we say that that is one particular bulb which will be on, and it would take us one move to off that particular bulb? Yes or no? Okay. Now, if this much is clear, guys, the only thing we need to check is if the number of ones is odd or not. If it is odd, then we will say that it will require one move, otherwise it won't. Is this much clear for everyone? Okay. If this much is clear for everyone, let's now go to maximum number of moves. Okay, max moves. Okay. Now, guys, we want to maximize the number of moves that we want. If we want to maximize the number of moves, here, guys, we want the number of bulbs to be as much on as possible. So do you agree we would like to pair 1 0 with a 1? Yes or no, guys? Like if we want to maximize the number of moves, we would like the bulbs to be on when they are given to us. So we would like to pair the ones with zeros because this is the only case when they are on. Is this much clear with you all? Okay. If this much is clear with you all, guys, if there are x zeros, okay, and if there are y ones, let's consider 1 1 1 0 0 0 and let's say 1 1. Okay. Do you agree, since we want to pair up zeros and ones, since there are 3 zeros and 5 ones, do you agree we can only pair them up like this, which is we can only have 3 bulbs, which is on. So it would take us 3 moves maximum, and this we will have to force together, and it would be off regardless. Yes or no, guys? So if we have x zeros and y ones, how many moves can we have? Or how many bulbs can we have which are on initially? Exactly. So we would like to have minimum of x comma y bulbs possible. Is this clear for everyone? Great. So if this is clear for everyone, guys, this is more or less the solution. So for minimum, we just need to print number of ones modulo 2. Basically, if it is odd, you print 1, otherwise you print 0. And for maximum, you just have to print minimum of number of ones, comma, number of zeros. That is more or less it for this solution. So let me show you the code for this. Okay. So if you look at the code, guys, I taken the switches array. I increment the number of ones whenever it's a 1, whenever it's a 0, I taken the number of zeros. So I print the minimum, which is 1 modulo 2, and maximum is minimum of 1 comma zeros. Is this clear for every single one of you all? You take an input in O of n, and then you can compute the answer in big O of 1 time. Okay. Great. If this much is indeed clear for every one of you all, let's move on to problem B. Okay, this is a good problem, and explanation of this will require some time, and it's a very, very beautiful and elegant problem. So what does this problem say, guys? You are given an array A, which is a permutation of 1 to n, and n is given to be odd. Okay, your task is to choose an odd positive integer m and split A into m subarrays B1, B2, Bm, such that for each element of the array, A belongs to exactly one subarray, and for all I from 1 to m, the size of that subarray is also odd. Once we have done this, the thing that we want to take care of is that if we have m particular subarrays, in that particular case, we would like that the median of all the medians of those subarrays is k. Let's start with understanding what the problem statement says. Okay, guys. So this is what the problem statement says. The problem statement says that you are given an array B of size n, and here n is odd. All right. Let's consider it 7 for now. Okay. Now, guys, we need to select an m such that m is also odd. Once we have done that, and these numbers are 1, 2, 3, 4, 5, 6, 7. Okay. This is the array. If we are given 7, this is the array that is given to us. We have to select a particular m such that m is odd. After that, and this can be anything. M can be greater than equal to 1. It doesn't really matter. This is completely our choice. Okay. Once this is done, we need to select m subarrays. Okay. Let's say we had to select 3 subarrays. So let's say we chose this one, and this one. The thing to take care of here is that the size of each subarray should be odd. So you can see that this size is 3, this size is 4, and this size is 3 again. Okay. Now we are asked to find the median of these subarrays. What does that mean, guys? The median of this subarray is 2. The median of this subarray is 4, and the median of this subarray is 6. The median of all these elements right here is 4. So that is what we can say is that 4 is the median of medians of this particular array. Okay. Now, the question asks us that the problem, we are given a particular k, we need to find such a configuration of the subarrays such that the median of the median is equal to k. Is this much clear for everyone? For people who weren't able to solve this, is the problem statement clear, guys? Like, we are given an array, we are given an odd m, we need to divide the array into m subarrays so that the length of each subarray is odd. Then you find the median of each of those subarrays. And after that is done, you find the median of all those elements. So you can see that the median here was 4. So we can say that the median of the median was 4. Now we are given an integer k. Our task is to find such a division of the subarrays such that the median of the median is equal to k. Is this much clear for everyone? Yes. Okay. So if this much is clear with everyone, let's go about how to solve this particular problem. Okay, guys. So let's have a look. The first thing to understand here is the nature of median. Okay. Keep in mind that the array is sorted here, which is 1, 2, 3, 4, 5, 6, 7. Okay. Guys, the first thing to notice is that a median of an array of odd length is the middle element. Okay. So the median of this particular array would be 4. Okay. Is this much clear for everyone? Like basic definition of the median. If this much is clear for everyone, guys, the first thing that we need to notice is that we need to select M, okay, which is odd, right? Now, if M is odd, guys, let's say M is equal to 3. If we chose this element as the first one, this element as the second one, and this element as the third one, okay, this subarrays, okay. Do you agree, guys, that let's say we have the median of the first subarray, which is median 1. Then we have median of the second subarray, which is median 2. And then we have median of the third subarray, which is median 3, which is here 1, here it is 2, and here it is 5. Can we say that median of 2 is greater than median of 1 and median of 3 is greater than median of 2? Yes or no, guys? Tell me. Because the array is sorted, do you all agree that the median of this subarray would be greater than the median of this subarray, and the median of this subarray would be greater than the median of this subarray? Put a yes in the chat, guys, if this much is indeed clear for you all. Okay. Now, if this much is clear for you all, do you notice that whatever we select M, okay, the median of the median is nothing but the median of the middle subarray. What do I mean by this? Here, guys, you can notice that you have elements, you have the medians as 1 to 5. The middle median, since we have three subarrays, the middle subarray is this one. Yes or no, guys? We have three subarrays. The middle one is the one with 2. Do you agree that the median of these medians is nothing but the median of the middle subarray? Yes or no? Similarly, let's consider we had 5 uh, instead of m is equal to 3. Let's say we chose m is equal to 5. So let's say we chose this one, this one, this one, this one, and this one. Okay. Now you can notice that our middle subarray is this one, and the median of this subarray is 4. So we can say that the median of our median is indeed 4. Is this idea clear with every one of y'all? Tell me, guys. Yes, great. If this much is clear with every one of y'all, now we need to come up with just a way so that, let's say let's say we have k, okay, we need to make our median k, okay. If we want to make our median k, guys, do you agree the median of the middle subarray should be k? Yes or no? Yes. Okay. Now, if the median of our middle element, median of our medians should be k, our median of our middle subarray should be k. So let's say k is equal to 4 here. So we can just fix this as it is. Okay, let's see how we can go about constructing it. So let's say k is equal to 4. We can say that, okay, this is going to be one subarray. Now, how many ever subarrays I create on this side, do you agree the same number of subarrays I will have to create on the left hand side as well? Because if there are x subarrays here and x subarrays here, this right here becomes the middle subarray. And since that is the only element in that subarray, it becomes the median of that subarray. So this is the only task that we want to do, is that you find k, and to the left hand side and to the right hand side, we want to distribute it to even number of, like, same number of subarrays. Is this idea clear with everyone? Tell me, guys. Do put a yes in the chat if this is indeed clear. Okay. So if this much is indeed clear with you all, guys, can you see that on both sides we have odd number of elements? So if on both sides we have odd number of elements, we can just select this and this as one of the subarrays and do what we want to do. Okay. Here you can see that the sizes of both of them were equal. All right. I think I came up with a more difficult, like more unintuitive solution in the uh, contest. I will explain my solution first and then the more optimized one. But guys, since both of these are odd, you can just select one, then you can print 4, and then you can print 5. This means that your one subarray was 1, 2, 3, your second subarray was 4, and your third subarray was 5, 6, 7. Okay. Now, let's change our approach. Okay. Let's say k is equal to 3. Okay. If guys k is equal to 3, let's see what happens. So 1, 2, 3, 4, 5, 6, 7. So we want our median to be 3. So we select this and say this is one of the subarrays. Now, guys, do you notice that on this side and this side, we want the same number of subarrays and the size of each subarray should be odd? Yes or no? Now, since on both sides the number of elements is even, do you agree I can select this one, I can select this one, and now the rest of the things are just of odd length? Yes or no, guys? Because an even element, let's say 2, can be split into sum of two odd elements, which is 1 and 1. And similarly, this 4 can be split into 1 plus 3. Is this idea clear with everyone? Okay. So, guys, that is more or less the optimal idea. That is, you are given a particular k. Okay. Let's say 1, 2, 3, 4, 5, 6, 7. Let's say you are given 3. Okay. You check how many elements are there to the left, you check how many elements are there to the right. If both of them are even, then you just split it into one element and rest of the elements, one element and rest of the elements, and this element itself. This partition would more or less work. Similarly, instead of even elements, if there are odd elements like 1, 2, 3, 4, 5, 6, 7, what we can do is, and let's say k is, let's say 4 here. So this is one of the things, and since both sides have odd, then we can just select this. Okay. But now, guys, here comes an edge case. Now, I think I want you all to point it out to me. Since on the left hand side and on the right hand side, we need some particular elements for which k would it not be possible? Exactly. If k is either 1 or k is either n, in that particular case, it is not really possible because here we don't have anything on the left and here we don't really have anything on the right. Is that much clear for everyone? Okay. Now there is something else that I did in the contest actually. What did I go about doing in the contest? In the contest, I just split everything into groups of one, e- except for the last group. What I'm trying to say by this is my solution is just, let's say for k is equal to 3, you have this. Okay. Then you can see that there are two groups here. So you need two groups here as well. So you make group of one, and then for all the rest of the elements, like you make group of one, and for all rest of the elements, you make one group. Okay, let me iterate over this again. Let's say we have 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say k is equal to uh, this right here, 4. So this is one of our subarrays. 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 So this is 1, this is 2, and the third one we can just combine. We can always be sure that the last one is always going to be odd because on both sides their parity is going to be the same. Is this much clear for everyone? Okay, so on the side where you have lesser number of elements, you just split it into groups of one. And on the side where you have more elements, you just split it into groups of one, and the last one you can take in entirety. Does this make sense? This was my solution, but the easier solution is what I explained. Let's have a look at the code for the same. Okay. So guys, if n is equal to 1, I just print 1 comma 1. I don't think like that is just one of the edge cases. Apart from that, if k is equal to 1 or k is equal to n, this is not really required. If k is equal to 1 or k is equal to n, you just print -1. Otherwise, the size of elements, how many are there? So in my approach, guys, you saw that, let me just take you back. So how many ever are there on the minimum side? So on the left hand side of 4, there are 3 elements, right hand side, there are 5 elements. So we are going to distribute it into 3 groups on each side plus the 4. So the number of sizes becomes uh, minimum of k minus 1 comma n minus k. That is the number of elements on each side. So minimum into 2 plus 1. And then what I do is I just print the size. And after that, I print the subarrays on the left hand side. Then I print the element itself. And then I print the elements on the right hand side. Is this much clear for everyone? Garv says like even, yes, that would also work. Okay. I think there is like, as I explained, there's a much simpler solution to this, but this also works that you just find minimum on left hand side, right hand side. The left hand side, you print all the elements, or like on the smaller side, you print all the elements, and on the right hand side, you print one element. But the last subarray, you just club in entirety. Is this solution clear for everyone? Great. So if this much is clear for everyone, let's move on to problem C. Problem C is actually a very standard problem, and we would be learning what the problem is about. Okay, guys. So you are given an array A of n elements A1, A2 up till AN. You can perform the following operation any number of times. Choose two integers I and j, where I comma j is smaller than n, and assign ai is equal to aj. You need to find the minimum number of operations required to make the array A satisfy the condition. For every pairwise distinct triplets, there exists a non-degenerate triangle with sides of lengths ax, ay, az such that it forms a non-degenerate triangle. Okay. So guys, what does the problem say? The problem says that we are given an array A, okay, of size n. All right. Now, I would really appreciate if you guys are also interactive with this. Now, guys, the problem says that we need to change some elements. And after changing some elements, if I choose any random three numbers, it can be random, like for any triplet, they should form a degenerate triangle. Now, what is the condition for degenerate triangle, guys? The largest side should be smaller than the sum of the other sides. Okay. This is the condition for a degenerate triangle, or the formula that is given to us in the problem. The same thing. Okay. We want to find the minimum number of changes to make in this array. Okay. Is the problem statement clear with everyone, guys? I think the problem statement is very clear. The task is how do we go about solving this? So let's take an example. Let's take 1, 2, 3, 4, 5, 6, 7. Okay. So 1, 2, 3, 5, 6, 7. Okay. So guys, whenever you come across such questions, the first thing you should ask yourself, if this array was 7, 1, 2, 3, 4, 5, 6, would it had made any difference? No, right? Like, does the order of elements really matter here? Is there anything said about indexes being sorted or something like that? No, right? So guys, the first thing you notice here is that order does not matter. Okay. Now, we have been told that order does not matter. This means that we can sort the array. Yes or no? Okay. Now, there is a very crucial observation. Like, this is fine. We can sort the array. So let's say we have sorted this entire array. Okay. Now, guys, consider the worst case triangle, which is 1, 2, and 7. Okay. 1 plus 2 is 3, which is smaller than 7, which makes a degenerate triangle. Basically, we cannot form this triangle. Yes or no? Yes. Now, guys, do you all agree that we would like to increase this 1, increase this 2, and Decrease this 7. Yes. Okay. So guys, if you look at a array which is not really degenerate, let's say we made this into 3, we made this into 3, and we made all these elements into, let's say, 5. Okay. Now guys, this remains sorted as it is. Okay. And do you notice that if you take the smallest element, the second smallest element, and the largest element, 3 plus 3 is greater than 5. So this forms a non-degenerate triangle. Okay. Guys, can you notice that if for the smallest or the worst pair, it forms a degenerate triangle, then any other triangle you try to form, either you will move the largest one towards the left, or you will move the smallest ones towards the right. So can we say that if for the smallest two numbers and the largest number, it is possible to make a non-degenerate triangle, then it is possible for any triplet in that particular array. If you look at any other pair like 3, 4, 5, 4, 5, 5, 4, 5, 5, so can you say that for any other triplet, it is possible? Yes. So guys, this is the main observation of this problem. And what is the main observation? That for if smallest plus second smallest, okay, greater than largest, then we can say that the entire array is valid. All right. Is this much clear for every one of y'all? Okay. If this much is indeed clear for every one of y'all, guys, do you notice? Okay, do you notice that here for this particular, we change this into a 3, we change this into a 3, we change this into a 5, and we change this into a 5. Do you notice that there was one subarray in the middle that we left unchanged, and all the elements towards the left, we made it equal to this element, and all the elements towards the right, we made it equal to this particular element. Yes or no? Do you guys agree? Okay. So guys, if you look at the most optimal structure, okay, we are given some array. We are going to choose some subarray, and we want it to be as large as possible. All elements on the left we make equal to this element, and all elements on the right we make equal to this element. And this right here should be a valid one. Yes or no? Yes or no, guys? Tell me. So our goal, okay, our goal is now to find the largest size, okay, largest size valid sub array. Yes or no, guys? Tell me. If we are able to find the largest size valid subarray, and let's say the size of that is x, do you agree we would just need to apply n minus x operations? Yes. So guys, do you notice that what we can do? Why am I saying this problem is standard? Finding this right here can be done very easily. And how do we do that? Let's consider we have an array 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. For all elements, for all indices, we are going to assume what happens when this is the start of my valid subarray. Like for each index, we are going to assume that, okay, if this was the start of the valid subarray that I chose, what is the maximum length that I can have? Let's assume that the smallest one is 1. Do you agree if the smallest one is 1, the second smallest has to be 2? Yes or no, guys? Okay. So the subarray starts here. we can have it till 3. No, we cannot have it till 3. We can only have it till 2 because 1 plus 2 is equal to 3. This is not valid. Okay, let's consider something else, something more random. Let's consider we start at 4. So if smallest is 4, second smallest is 5. For 6, is it possible? Can we have 4, 5, 6 as valid? Yes. Can we have 4, 5, 6, 7 as valid? Can we have 4, 5, 6, 7, 8 as valid? But can we have 4, 5, 6, 7, 8, 9 as valid? Okay. So guys, do you see that this right here is a predicate function which is true up till a certain point and then it becomes false? So for every particular index, we can fix the start point of the valid subarray, and then we can binary search to find the farthest index j such that index I to j is a valid subarray. Yes or no, guys? And since the array is sorted, then just binary search upon it. Does this make sense? So that is more or less it for this solution. It is a big O of n log n solution because we first sort our array and then for each index, we just binary search for the length and we just store the maximum possible length. Let me show you the code for the same. It could have been done using 2 pointers as well, but uh, that is okay. So guys, you take in the array, you sort it, then you say that, okay, our answer is initially n. And then we assume that index I is the starting point and we go till the second last element. So because the smallest and we need the second smallest. So left is equal to I plus 1, right is n minus 1, and index is I plus 1. While left smaller than equal to right, mid, and then if AI plus 1 is greater than a mid, then index is equal to mid, left is equal to mid plus 1. Otherwise, right is equal to mid minus 1. Now, guys, if we have the length of the subarray, I did say that n minus size would be the number of operations required. So answer is equal to minimum of answer comma n minus size of the subarray. Now, how do I know the size of the subarray? If the ending index is j and starting index is I, the size is j minus I plus 1. Is this much clear for everyone? Okay, so this is a very standard problem. The only interesting observation in this problem was that for a particular subarray, if the smallest plus second smallest is greater than the largest, then for any other triplet, it would also be valid. Basically, we would also be able to make a non-degenerate triangle. So that is the only condition that we needed to think of. Is this much clear? Amazing. If this much is indeed clear with every one of y'all, let's move on to problem D. So guys, problem D was today ad hoc and it was very, very interesting. It was like trees was involved, but it was nothing around trees. Gurkirat says, what was the intuition of this? Intuition of what, Gurkirat? Nishwan says,
Problem,
please share. Yes.
problem C.
So the first thing you notice is that you need to sort the array, right? And like that is the first thing that matters. Like this is a very like the first thing is you can sort the array because it won't change anything. Okay. If this much is clear, after sorting the array, uh, you would intuitively go to check if it is valid or not, and you will start with the smallest pair, right? Smallest, second smallest, and largest, because that's the most extreme case.
या
Okay.
एक्चुअली शॉर्ट तक तो मैंने सोच लिया था पर मैं थोड़ा 2 पॉइंटर की तरह सोच रहा था तो उस तरीके से कैसे हो सकता है.
No, no, like this can be solved using 2 pointers. Like if the idea is clear, converting binary search to 2 pointers is doable. Maybe I will share the link in the comments of the live stream. But once you sort the array, the first thing to notice is that the extreme case is the smallest, second smallest, and largest one, correct?
Yes, sir.
Okay. Now, if this much is clear, do you notice that for any other pair, either the smallest is going to increase or the largest is going to decrease, correct?
Yes.
So if the smallest is going to increase, it is still going to stay valid. And if the largest is going to decrease, it would still stay valid, right? Like if you look at the equation that we are forming, which is x plus, one second, x plus y is greater than z. If you
Mhm.
reduce z or you increase x or y, this still remains valid, correct?
Yeah.
So that is
Okay.
why if you say that for the smallest and second smallest and the largest, if it is valid, then for the entire array, it is valid. Okay.
Okay.
And then after that, if this much is clear, you will kind of notice that you will have to fix some particular subarray. Like there are going to be some elements that you do not change, and all the elements towards the left and all the elements towards the right, you would bring towards them. Now, if this much, like if you gain this intuition, that okay, like for a particular subarray it is valid, if this much is true, then okay, I do not need to change all elements, I would like to fix a subarray and then bring all elements towards this. It's just like the median problem, you would say, where you need to make all elements equal, in that you try to bring the largest down and the smallest up. So similarly in this case you would like to do something similar, and once that much is clear, then it is just a standard two pointers or binary search technique that you can use to find whatever is required. Okay,
Okay. Thank you, sir.
great, amazing. Now, guys, if this much is indeed clear for everyone, let's move on to Genokraken, which is one of my favorite problems. Okay, upon clearing waterside area, Gretel found a monster. Okay, this much is just useless. So what does the problem say? You're given a tree of n nodes that we don't know yet. Okay, like uh, these are not valid. Let's say this is a tree. We don't know this tree, and like we know how many nodes are there, but and we have to guess this particular tree. There are some special properties about this tree. That is, okay, the special properties about this tree are, if we remove node 0 and all adjacent edges, this tree will turn into a forest consisting of only paths. What does this mean, guys? If you look at this tree, if you remove node 0 and all its edges, do you see all other nodes, all other connected components form a bamboo kind of structure, which is like straight line from 3 to 8, straight line 1 to 4, and straight line 2? Yes. So this is the first property of the tree. Guys, then the second property of the tree says that for every parent, okay, if x is smaller than equal to y, then parent of x is smaller than equal to parent of y. Basically, if you have two indexes I and j, where I is greater than smaller than equal to j, then parent of I will also be smaller than equal to parent of j. What does this mean? Like if let's take any two random nodes, let's take 4 and let's take 7. So since 4 is smaller than equal to 7, the parent of 4 is going to be smaller than equal to parent of 7. Similarly, if you look at, let's say, 2 and 5, the parent of 2 is going to be smaller than equal to parent of 5, which is 0 and 3 respectively. Okay. Now, there is one more special thing, and this is the one which most people would have missed or not understood the importance of. Node 1 has exactly two adjacent children. Okay. What does this mean, guys? That node 1 is going to have this edge, which is to 0, and node 1 is also going to have one child. Yes or no, guys? Tell me. If node 1 has two adjacent nodes, can we say that node 1 is going to have its connection with its parent, which is 0, and then one child, and we are guaranteed this? Can we say this, guys? Okay. So, guys, let's consider this as an example tree. Our goal is to find this particular tree, and to find this tree, we need to do some queries. Like if we query A and B, what do we find? Right? You can query any nodes A and B which are greater than 0. Let's say you query 1 and 2. You will be returned 1 if there is a 0 in the path from 1 to 2. Otherwise, you will be returned 0 if there is no path between 1 to 2. Okay. So this is the problem which is given to us. We are said that we need to find the tree in 2n minus 6 queries. So let's look at the solution of the same. So let me draw an example tree. Okay. 0, 1, 2, 3. Let's say we have 4, 5, 6, 7, 8, 9, 10. Okay. So guys, I would like to break this problem down into two possible ways. Like first, we need to find the properties of this tree. And second thing, we need to find how we can find this particular tree. Okay. So guys, what are the properties? The first property is if you remove these edges and this node, you will find only straight bamboos. Okay. Apart from this, the node 1 is going to have exactly two adjacent nodes. Okay. The second thing, parent of I is smaller than I. And for two nodes x comma y, where x is smaller than equal to y, parent of x is smaller than equal to parent of y. Okay. So, guys, do you agree that for a particular node I, its parents can only be 0, 1, so on and so forth up till I minus 1? Yes or no? Tell me, guys. Put a yes in the chat if this much is indeed clear for y'all. If not, do let me know what is not clear. Okay, great. So, guys, for node 1, it is for sure that this edge is going to exist between 0 to 1. Okay. Now, we are also said that node 1 for sure is going to have a child. For sure, it is going to have a child. And apart from that, rest other things form a bamboo structure. Okay. Now, guys, here is where the first observation comes into play, and it is one of the most critical for this problem. We are said that node 1 is going to have a child. Okay. Now, guys, let me remove everything else. Let's say this node is 1. Let's say this node is x. Okay. Do you agree, guys? P of x is equal to 1. Correct? Okay. Now, guys, if P of x is equal to 1, for all other nodes from 1 to x minus 1, can we say that P of x is equal to 0? Because one node can only have one child. Because, guys, if it has two children, it doesn't form a bamboo structure. So each node can only have one child. Okay. So if P of x is equal to indeed 1, do you guys notice that for all nodes from 1 to x minus 1, the parent of all those nodes will be indeed 0? which is from 1 to 3, can you notice that the parent of those nodes is 0? Okay. Now, if this much is clear, let's actually do this. Okay. Because we already know that 0 is not going to have any parents and 1 is going to have parent equal to 0. So guys, we'll just run a while loop. Okay. Let's say we have a while true loop. We ask I comma 1. Okay. If we ask I comma 1, guys, let's say for 2, do you agree we'll be returned a 1 because the path from 2 to 1 is 2 to 0 to 1. So we'll be returned a 1. So we know that the parent of 2 is 0. Similarly, we can ask 3 to 1. So guys, when we ask 3 to 1, let me use some other color. Let's say light green. Okay. This is too blending. This. So when we ask 3 to 1, we'll be again returned 1 because 0 is in the path. But guys, when we ask 4 to 1, do you agree we'll be returned a 0? Yes or no? Because since 4 is the child of 1, we do not really pass through the 0 and we'll be returned a 0. So the first part of the solution is that we are just finding this particular node. And keep in mind, worst case, this is going to take n minus 2 iterations, which is the complete tree. Okay. So we are iterating through nodes, checking if its parent is 1 or not. If its parent is 1, we break and we have found the node X. Correct? So do you agree we have sort of formed this, we have found this part of the tree? Yes or no, guys? Let me show you this much of the solution. Okay. So we have a parent vector and while index smaller than n and ask index 1 is equal to 1, index plus plus. And in the end, if index is smaller than n, parent of index is equal to 1. This is the only thing we do, and we are able to find the element where the parent of that element is 1. Clear for everyone? Put a yes in the chat if this is indeed clear. Okay. Now, guys, if this is indeed clear for everyone, do you agree, okay, that we have some leaf nodes now? We have leaf 2, we have leaf 3, and we have leaf 4. Basically, for all the elements, okay, let me just show you all. For all the elements from 2 to X, these are now leaves. Consider that this tree has not been found yet. These are now leaves. Correct? So guys, if these all are now leaves, let's say we want to find the parent of 5. Okay. We'll start with the smallest possible leaf, which is 2. Okay. Now guys, if it is actually the parent, then 2 comma 5 will return a 0 because there is no 0 in the path. But otherwise, you can see that if I ask 3 comma 5 or 4 comma 5 will be returned 1 because there is 1 in the path. Okay. So if for 5, you can see that if we ask 2 comma 5, we get returned 0. So for 2 comma 5, we get returned 0. So can we say 5 is the child of 2? Yes or no, guys? Yes. Yes, right. Okay. Now, if this is the case, okay, so we'll look at elements. Okay, we'll look at so this is not a valid tree. So sorry for that. Like this is not valid. I think we'll make this 6 and we'll make this 7, 8, 9, 10. I think this would be valid. Okay. Now we found that the parent of 5 is 2. So guys, we found this. Now what are the leaves that are there? You can see that the leaves that are now there for this tree are 3 5 and 4. Yes or no? Now, let's say we want to find the child of 6. Okay. And 6 is, let's say, here instead of here. Okay. Consider this is the sort of tree that is there and there is nothing over here. Okay. And this is 8. So, guys, do you notice that we'll ask 6 comma 3? If we ask 6 comma 3, we'll be returned a 1. Yes or no? It means that 6 is not the child of 3. But guys, do you agree, since 6 is not the child of 3, its parent is either going to be 5 or its parent is either going to be 4? Yes or no? So, if the parent of 6 is going to be either 5 or 4, can the parent of 7 or 8 ever be 3? No, right? Because here is the second observation that was given to us. If x smaller than equal to y, then parent of x is smaller than equal to parent of y. So for 7 or 8, the parent cannot be 3. So we can discard this completely. Okay. Now, we'll ask 6 comma 4. Now, guys, 6 comma 4 will return a 0. So we can say that, okay, we have formed this tree and we have knowledge of this particular tree. Okay. Now, we'll remove 4 as well because the leaf that was formed was 6. And these are the two uh, contender parents we have. Now for 7, similarly, we'll start with 5. If we get returned a 0, okay, this is the parent. Otherwise, if we don't get returned this as the parent, we can just say that it's never possible to have this parent for any other node and we can discard this. So for 7, we'll ask 5 comma 7, it returns 0. So we can say that parent of 7 is 5. And then we will put this as 6 comma 7. And after that, for 8, we'll iterate through 6. So for 6, it returns a 1. So we can say that for 6, it's not possible for 8 or any nodes further. Then we'll go to 7. So 7 comma 8 returns a 0. So we can say that the parent of 8 is 7. Is this much clear for everyone? So let me just reiterate over what we did. Guys, is it clear that we are finding? Yes, I'll show you guys. So what are we doing? We have formed our particular tree, which is 0 to 1 to 2, 3, and 4. Okay, this is the tree that we have found. And let's say we are finding the parent of 5. Do you agree the contender parents are 2, 3, and 4? Yes or no? 2, 3, and 4. Okay. So we ask the queries 2 comma 5. If it returns a 1, it means that the parent of 5 is not 2. Okay, similarly, let's say we ask 3 comma 4, it returned as 1. It means that the parent of 5 is not 3. Let's say we asked 5 comma 4, it returned as a 0. It means that the parent of 5 is 4. Correct? Yes or no, guys? Tell me. Yes. Now, the thing to notice is that for 6, can the parent of 6 be 2 or 3? If it is, would it not satisfy this? Yes or no, guys? So for 5, if it is not possible to have parents 3 and 2, then for 6, 7, 8, 9, 10 also, these parents are not possible because they would contradict the statement that is given to us. Yes or no? So we can discard these parents, and after that, since for 4, we added the child 5, do you agree we'll have to change this 4 to a 5 because 4 is no longer the leaf, 5 is the leaf? Yes? Okay. I hope this much is clear. But now, guys, there is one small optimization. If you look at this, like there is one small optimization that you can do. If you look at all the set of nodes, okay, if I ask 5 comma 2 and 5 comma 3 and I get returned 1 1, do I need to really ask 5 comma 4? Isn't it obvious that it is going to be 5 comma 4? What I'm trying to say is, guys, the valid parents we have is 2, 3, 4. If we ask for all the parents except 1, and for everything we get 1, 1, 1, then for the last one, we don't really need to ask because we are sure that this is going to be the parent. And what is the last element, guys? If I am searching 5, do you agree the last element is nothing but I minus 1? So for all elements except the last one, if it is not valid, then we can say that I minus 1 is the parent. Is the approach now clear to everyone? Yes? If it is now clear, guys, let's move on to the implementation. So guys, we are inserting all the valid parents into a set, which is from 2 to index. Now you can notice that I'm not inserting index because when I go for index plus 1, if anything is not valid, then I can just say that index will be the parent for index plus 1. So I insert all the possible parents into a set. Okay, then I say that currently parent of index is parent of I is I minus 1, basically the default case. Now I have a vector 2 erase. Basically, I want to remove all those elements that are not possible to be parents further on. Okay. So I iterate through the parents and I push them into my uh, vector. Okay. Because even if I ask it and it returns 0, it won't be parent for any other elements because the leaf would update. Okay. So we keep iterating, and if ask of I comma j is equal to 0, it means that parent of I is equal to j, and then we break. Otherwise, we do nothing. We just keep iterating. Okay. After that, we iterate through two arrays and erase I. And after that, guys, if parent of I is not equal to I minus 1, now we are going to the next element. So for the next element, the obvious parent would be the current I. And since here I have not inserted I minus 1, I am just inserting I minus 1 if it is not the parent of I. Is this much clear for everyone? So that is all that you needed to do to solve this particular problem. Like, this problem is divided into two tasks. First is finding the index for which the parent of that node is 1. After that is done, you can use a greedy strategy, that is iterate through all the possible parents, and if you have found the parent of the particular node, remove all those nodes that are before this particular node, and once that is done, you can update the new possible parents and move on to the next node. Okay. Is the solution clear for everyone, guys? And why does this work in, let's say, 2 and minus 6? The first thing to notice is that for each particular node, we are going to get one query where we get I comma j is equal to 0. So this will be n minus 2. And after that, do you agree that each element from the parent vector will be erased exactly once? Like if you get a 1, ask I comma j is equal to 1, that element is gone. Like if it is not the parent, it's just gone, discarded. So each element gets discarded exactly once, and that is why uh, it is bounded by 2n minus 2. And because we are not asking the last element, that is why we reduce it even further, which makes it run in 2n less than 2n minus 6. Kushal says that, are we storing leaf nodes in parents? Yes, Kushal. We are storing the current leaf nodes of the tree formed in our parents set. Okay. Is this clear for everyone? Was this particularly hard? Like, yes, coming up with the solution is relatively tough. It is a kind of smart-ish solution which does not involve any algorithm. It's just a It's just like a puzzle that is supposed to be solved. But is this clear for everyone? Great. If this much is clear for everyone, that is more or less it. I hope you liked today's session. And thanks a lot for watching. Happy Diwali once again. All the best for ICPC and see you guys next time. Till then, bye bye.